The first thing that it's important to notice in this problem is that, again, we have a velocity versus time graph. And that means that any questions that come up about acceleration are, in essence, asking a question about the slope. Questions about the velocity have to do with questions about the height of the function in question. And any issues regarding position, net displacement, total distance traveled, things of that nature are all going to be dealing with the assigned areas beneath the curve. So, part A, we have to find the acceleration of the particle at time t. At time t equals 3, rather. So a of 3. Now, this is a calculation that can be done numerically. In fact, the second thing that is interesting about this problem is that this entire question, all 4 parts of it, can be done entirely numerically. Let's see just where that takes us. So here we have the calculator. The first thing we want to do is to input the function. And as you can see, I've already placed that in there into y1. It's very important that you learn to put the function in once, and then in all the calculations that you do in subsequent subsections of the question, that you simply reference that function rather than typing in the function time and time again. And so our first question is about the acceleration, and so we just have to invoke the inderiv function, which we can find in the catalog by scrolling, or rather jumping down to n, and then scrolling the rest of the way down. And then, of course, we need to remember what inputs it takes. The first thing in this representation is it needs to know with respect to what variable. Even though the problem statement is in terms of time, because we've put the function in the calculator in terms of x, then we have to input x here. Now we need to input the function. Again, rather than rewriting it every time, we're just going to go to vars, choose yvars, function, and y1. That inputs the function. Lastly, we just put in the time that we need to evaluate it at, and that's at t equals 3. But again, as we said previously, because we've encoded the function in terms of x, it's at x equals 3. And we get an answer, negative 5.46675. And it never hurts to write a couple of extra decimal places past the 3 that are required. So just a little explanation we'll write here. This is the result of numerically evaluating the slope of the tangent line of the velocity function at t equals 3. We do have to add this sort of a statement. We can't just write the answer. We have to make it clear to those that are grading it that we understand where we get this answer from. Part B asks for the total distance traveled. And again, a light bulb should go off in your brain when you see the phrase total distance traveled. Is the same as the sum of the absolute value of the signed areas under the curve from t equals 0 to t equals 3. Again, we can evaluate that numerically. And there we're going to use the FNINT function. So what we want is, again, go to the catalog, jump down to the F category, scroll down to FNINT, and input, depending on which version of the calculator you have. The sequence in which you order the variables may differ, but the numbers are the same. So first from 0 up to 3 of, what's the function? It's the absolute value. We get absolute value. It's the very first thing in the catalog. So we want the absolute value of our original function. Again, do that through vars so that we don't have to retype it. Not only does that save time, it reduces the chances that you'll make an error. And finally, with respect to what variable, and even though in the problem it's with respect to time, because we encoded the velocity function in terms of x on the calculator, we have to say it's with respect to x. And our answer is, this takes a little longer in the emulator, in the desktop version of the calculator than it actually does on the calculator, but our answer is 1.70241. So we can just write that in. Evaluating numerically, this equals 1.70241. Okay, we turn to part C. And this asks for the position of the particle at time t equals 3. Well, position, again, at a particular point in time is just the position at some known position and time pair. And in this case, they told us the position at time t equals 0 plus the sum of all the signed areas. Here we're not choosing the absolute value because this is about net displacement from t equals 0 to t equals 3. Again, we can do this calculation numerically, remembering that the initial position at t equals 0 was already given. That's 5. And then we use the calculator to find the additional distance. We will go in, jump down to F, and then painstakingly scroll our way down to FNINT. And again, we're going through all the signed areas from 0 to 3 of the function. Now we're just going to use the function itself, not its absolute value. We do that through vars, so we don't have to enter it more than once. And because we express the function in terms of x, we say that our variable is x. 0.77356, we add that on to the 5, and we have 0.77356. So our final answer is 5.77356. Part D wants to know when it is that the particle is farthest to the right. So let's think about what our possibilities are. First of all, it's possible that it could be farthest to the right just at the very beginning, right when t equals 0. Now, all of this area under this curve is going to be positive. This signed area is going to come out positive. And that's an indicator that the velocity is positive, and therefore the particle is moving to the right. So it keeps increasing through all of this signed area until it gets to this point. So we'll need to know what that point is in time, and then we can find out the distance that the particle is at that point in time. Now the particle starts moving to the left, as indicated by the negative velocity. So this is clearly not going to be a place where it's going to be farthest to the right. Our next candidate position is when it starts moving to the right again, which happens all the way from here to here. So we'll need to know this point. And then it's also possible, here it moves to the left, but now it again moves to the right. So it's also possible that the answer is going to occur at this point. So we need to find each of these time values and then test what their resulting distance value is to find out which one is farthest to the right. So let's see what we would have to say in words on a problem like that. We'd say the rightmost position candidates are at the t equals 0 start point, as well as each of the places on the velocity curve where the velocity changes from positive to negative. We'll use this phrase, evaluating numerically. And now we'll make a table. The times that we need to consider and the distance. Let's not call it distance. Let's say position, because we want to find farthest to the right, meaning if we get a positive number here, it's to the right. If we get a negative number here, it's to the left. Well, at t equals 0, we know that the position is 5, but now we need to find these other 3 points. Again, we make recourse to the calculator. What we ask it to do is find for us the intersection with the x-axis, or to put it differently, the zeros of this function. And so we'll graph it, and then we'll ask it to find the 0. It asks for our initial left-bound guess, and we know that we want this first place where the function crosses from positive velocity to negative velocity, so that'll be our left bound. This becomes our right bound. For a guess, we just put in the right bound. No need for us to have to do that work. And we get that the 0 is at 1.77245. So we can fill that in. 77245. Now we need to find the position that corresponds to t equals 1.77245. And so that's going to be the initial position, as we said. The initial position is just 5. And then we'll need to add in the sum of the signed areas. We'll go and use the FNINT function. Jump down to F. Scroll down to FNINT. And we need to go from our starting time of 0. And then we have to put in the value that we got, 1.77245, as our ending time. Our function, again, is the one that we've entered just once, and we make reference to it through the vars. And finally, our work is all done with respect to the x variable. So we get 5.89483. Where this time was 1.77245. Well, again, we have to go through this process to find each of these 2 points. There's no need to step through that again. I'll just write out what the answer comes out to. Here it's 3.06988. I'm sorry, 998. And here it's 3.96332. 3.06998. 3.96332. And the corresponding distances, again, doing the same calculation that we just went through for the first point, we get 5.78825 and 5.75244. Now we can pick our winners, namely the farthest from the right winner is 5.89483, and that occurs at 1.77245. So just to make sure we get full credit from these graders, let's write out thus the particle is farthest to the right when t equals 1.77245. It may be that we need to, in fact, not just talk about what the numerical evaluation, but what we were evaluating. And again, that's similar to this calculation. Okay, we just say that x of t for these different candidates, try the candidate times, that x of t is x of 0 plus the sum of the signed areas. Again, I want to emphasize, as I said at the beginning, notice that this entire question, all 4 subparts, is done without doing anything symbolically. The entire calculation can be done numerically. And just to be on the safe side, I always put in 5 places after the decimal point.